In this video, I'm going to describe the summary that I provide in this part of the textbook related to the three different approaches to conducting a one-sample t-test. Now, I should admit that I have reservations about presenting this type of material in a textbook, especially early on, because the risk is that people will get confused thinking the one-sample t-test is three different tests. It's not. It's actually one test. And the reason I include this material is that if you actually understand this material, then you'll really have a fundamental understanding of statistics, and that'll carry well with you as you move forward in the textbook. So the first approach is estimating the 95% confidence intervals associated with the difference between the sample mean and the non-sample mean. That was the first approach that I tested with respect to the hypothesis that there might not be a difference between my long-held impression that people sleep on average 8 hours a night versus the sample mean of 7.31, which comes from Kripke et al.'s study. And the difference amounts to negative 0.69. So my estimate is larger than Kripke's, so that comes out as a negative 0.69. And because the 95% lower bound and the 95% confidence interval upper bound are both in the negatives, they're both in the same direction, then we would conclude that there is in fact a statistically significant difference between my long-held impression and Kripke et al.'s estimate of 7.31. So it looks like I made a mistake, and I admit it as such in the textbook. Now the second approach, and this is a bit busy, but this is the t-value approach. This is where the t-value ratio, the difference between the sample mean and the non-sample mean divided by the standard error of the mean. Again, this is fundamentally identical to the first approach. And what we get here is a t-value, so the difference between the mean and the non-sample mean equal to 0.69 negative, divided by the standard error of the mean, which is 0.11, and that gives a t-value of negative 6.27, and that provided a p-value that corresponds identically to the result obtained with respect to the 95% confidence interval. There is, in fact, with a certain level of probability, I can't remember the p-value I estimated for this, but whatever it was less than 0.05, and that again rejects the null hypothesis of no difference between my long-held impression that people sleep 8 hours and Kripke et al.'s sample mean estimate of 7.31 based on a sample size of 100. Now the last approach that I mentioned is the 95% confidence intervals associated with the sample mean that Kripke et al. Estimated, which was 7.31. We can also test the one-sample t-test hypothesis, that approach as well. And in the textbook, I write that out such that the 95% confidence interval, lower bound for a mean of 7.31 with a sample size of 100, which means degrees of freedom of 99, is equal to 7.09. And the upper bound confidence interval for Kripke et al.'s estimate of 7.31, based on a sample size of 100, the upper bound is 7.53. And I mentioned that because these two estimates, the lower bound and the upper bound, do not intersect with my long-held impression, which is the non-sample mean, in this case 8, because they do not intersect with 8, we can logically conclude that there is a statistically significant difference between Kripke et al.'s estimate of 7.31 and my long-held impression of 8 hours asleep per night. Now I'm going to show this in a graphical form, so to me this actually captures what's going on. So here is the sample mean of 7.31 along the x-axis here. We can see it goes from 7 all the way to 8. And we have the Kripke et al. Sample mean of 7.31. And we have my long-held impression of 8 hours per night over here on the further end of the x-axis. And here's the lower bound, something like 7.1, and the upper bound, which is about 7.53, I think it was. We can go back here, 7.53 exactly. So this value here is 7.53, and because this upper bound did not go further than 8, then we can conclude that there's a statistically significant difference between the sample mean provided by Kripke and my long-held impression of 8 hours per night, which is the non-sample mean. Now here I've got a similar graph, but I've got it presented based on the mean difference between Kripke et al.'s 7.31 and my long-held impression of 8, and you might recall that was negative 0.69. So that's on this area of the x-axis, and the upper bound confidence interval goes up to something like negative 0.54, something like that. And the lower bound is a little bit more than negative 0.91, something like that, negative 0.91. And because these confidence intervals do not intersect with 0, which is the null hypothesis, there's no difference between my long-held impression, non-sample mean of 8, and the sample mean, because it doesn't intersect with 0, it is statistically significantly different from 0. These are saying exactly the same thing, but expressed in a slightly different metric, if you will. This is based exclusively on the sample mean, and it's not intersecting with the non-sample mean. This is represented as the difference between the sample mean and the non-sample mean, and this is the 95% confidence interval. And because that's not intersecting with 0, it is statistically significantly different from 0. Now I should say that whether your values are negative or positive is irrelevant for the expression not intersecting with 0. Hypothetically, I could have subtracted 7.31 from 8 and obtain a positive value, and the same logic applies so long as the 95% confidence intervals, whatever it is, the lower bound or the upper bound, so long as it's not intersecting with 0, then you would conclude with 95% probability that there is a difference between the means in the context of repeated sampling from the frequentist perspective. So those are the three approaches to testing the hypothesis that there's a difference between a non-sample mean and a sample mean, the alternative hypothesis, or stated alternatively that there is no difference, which is the null hypothesis. And in this case, with a sample size of 100, the null hypothesis was rejected.